Hello, my name is Dana Zini. I'll be giving a talk on our paper, Polarization Multi-Image Synthesis with Birefringent Metasurfaces. This work was done under my advisors Federico Capasso and Todd Ziegler at the Harvard University School of Engineering and Applied Sciences. The motivation for this work is based on the simple idea that all computational imaging tasks benefit from the capture and processing of multiple images. Now, this refers to sets of images that are captured from the same viewpoint, meaning the same camera location, but with different optics. Although historically is also referred to the second idea of multiple images captured from different viewpoints in different locations. Throughout this talk, however, we will only be focusing on this first case of multiple images. Now again, the idea is that if we want to extract additional information about the scene using our camera, say a depth map, segmentation mask, or hyperspectral data cubes, we can do so with simpler algorithms, less trained data, and often better accuracy if we are processing a set of distinct images instead of just one. Now, this paradigm of computing on multiple images has appeared throughout the long history of computational imaging. As a concrete example, you can observe its application to a task of depth sensing from defocused images. The camera shown on the right end contains a deformable lens paired with a standard photosensor. By applying a voltage, the shape of the lens is physically deformed and its focal length is shifted to different depths. One can then obtain a set of coded measurements by capturing multiple images sequentially over time while deforming the lens. Pulled from the original paper, you can see an example of two images, I0 and I1, that are measured for a static scene. When a pair of images are passed to a post-processing algorithm, you can obtain a depth map for orders of magnitude less computation. As one additional example, this paradigm is also applied to hyperspectral imaging. Here, the dynamic optic is instead a spatial light modulator, and by changing this component, different spectral filters can be applied to the captured images. Using a set of measurements taken sequentially over time, one can again reconstruct the hyperspectral data cube for the static scene with less computation and better accuracy than if you're using a single image. Now, these previous methods all captured multiple images sequentially over time. However, there's substantial interest in designing an architecture that can instead obtain the set of multiple images in a single exposure, in other words, a single snapshot from the camera. The benefit is that we could then apply these algorithms to scenes that are not static, and we can extract information with higher effective frame rates. One way to do this is with the general paradigm of using wavelengths as separate imaging channels. Now, in this work, I classify imaging systems that use this idea as snapshot spectral multi-coded imaging systems. And more generally, we've observed that systems that fall under this category have been heavily researched and developed for at least 30 years now. The general design of these cameras can be summarized in the following schematic. Some spatially varying spectral modulator is placed at the aperture plane in front of a focusing lens. This optic is essentially a wavelength-dependent phase or transmission mask, and it serves the purpose of producing distinctly coded images on different wavelengths of light. These images are of course spatially overlapping at the photosensor plane, and so a mosaic of complementary spectral filters tiled above the sensor pixels are then used to simultaneously measure and demultiplex the signal. The most common case is the use of a Bayer color filter in typical RGB cameras. To give an example of what this optical component might look like in real life, it could be as simple as spectral filters at different locations in front of the lens, although there are many other examples historically. Using this optic, the authors referenced below capture a measurement that is then demosaiced to obtain three distinctly coded images on the RGB channel. These images are then passed to post-processing algorithm to obtain a segmentation mask and depth map efficiently. So this idea of spectrally encoding multiple images and measuring them in a single snapshot using a detector-side filter array has been applied to many tasks, not just depth and segmentation. However, the development of new technology has now opened the door for a different way to approach the same problem. Specifically, there's an opportunity to now consider the paradigm of using polarization as distinct and multiplexed imaging channels. The general schematic for these systems is very similar, but instead of a mosaic of spectral filters above the photosensor's pixels, we now employ an array of linear polarizers. Analogous to before, we classify systems as type as snapshot polarization multi-coded imaging systems. It is worth knowing that photosensors with a 2x2 tiling of polarizers at 4 different angles, as shown here, have become commercially available over the last 5 years and can be purchased at just about any optics retailer. Paired with a focusing lens, we can then consider to utilize a spatially varying polarization mask instead of a spectral mask, which results in distinct images carried on different polarization states. Although there are a number of advantages in considering the use of polarization, either in place of or in conjunction with spectral coding, systems of design have surprisingly been largely unexplored. To date, there's only one other work at the time of its publication that has considered designing a multi-image computational system of this form, and that is from this group referenced below at Rice University. Now, although the imaging system has a slightly different setup, it's instructive to view it in the form as shown here. Their optic consisted of two linear polarizers that transmits either 0 or 90 degrees polarized light. And these two polarizers are then placed on two different halves of a phase mask. After measuring and demosaic the intensity at the photosensor, two of the four images, let's refer to them as I0 and I90, are used with a reconstruction algorithm here to obtain super resolution depth maps. By having two optically coded images instead of just one, the authors again demonstrate substantial improvements in accuracy relative to single imaging systems. Now, the heart of this work is to delve deeper into systems of this type and to present it more formally. In doing so, we try to raise and answer two fundamental questions. The first is, can we design and utilize all four polarization channels instead of just two for imaging tasks, and is there a motivation to do so? And the second question is, what are the general capabilities and potentials for systems that leverage this type of design? Now, in order to answer this question about the capabilities and potentials of optical systems like this, we need to first frame this design in terms of some particular choice for the optics. And in this work, we propose the use of dielectric metasurfaces, occasionally preceded by a spectral filter or linear polarizer to simplify the discussion. The metasurface combines the role of both the focusing lens and the optical modulator into one single, ultra-thin flat optic lens, and is perhaps singularly capable in its ability to produce spatially varying polarization transformations. Metasurfaces are a new class of recently matured optical elements that consist of carefully engineered nanostructures patterned on the surface of a flat, transparent substrate. An image of a real metasurface is shown here, captured using a scanning electron microscope, since the size of the pattern structures are smaller than the wavelength of light. The key idea of a metasurface is that the phase delay imparted to an incident wavefront that passes through the nanostructure depends on the shape of the structure. By changing the shape at a given location, we can change the phase delay and to a lesser extent the amount of light that is transmitted at that spot. Importantly, if the nanostructure shape is anisotropic, like with the nanofins used in this work, then the phase delay in transmittance becomes polarization dependent. And by judiciously selecting the nanostructure that is placed at each location across the lens, we can then structure the entire incident wavefront such that it gets focused to a single point of the photosensor or to form user-defined intensity patterns. Now, we know that the shape of the nanostructure generally defines its optical response, but how do we quantify it exactly? To do this, we have to consider each possible nanostructure shape in isolation and compute its interaction with light by solving Maxwell's equations. Specifically, we use a field solver to create a dataset mapping the nanostructure shape, in this case the width of the nanofin along two directions, to its phase delay and transmittance that is imparted to two polarization states. A slice from this dataset is shown here, where each point corresponds to a different nanofin instantiation. As a note which will come up again later, this optical response is also strongly wavelength dependent in a way that is unique for each nanostructure, and so we have to run this simulation for all wavelengths that we want to consider. Using this dataset, we can define what a metasurface composed of nanofins does in terms of functionality, but it doesn't give us immediately any method to design the device or to optimize its performance. This ability is of course necessary if we want to probe the capabilities of the system for a given task. In order to enable gradient-based optimization of our lens alongside our post-processing algorithms, we need to introduce a differentiable representation for this mapping. In this work, we also propose the use of a simple MLP, also known as a multi-layer perceptron, to learn the mapping between nanostructure shapes and the optical response, as shown here. We find that a simple design with just two hidden layers and regular activation is sufficient to almost perfectly reproduce this mapping. Here you can visually compare the MLP predictions on an upsampled grid to the coarsely swept training data. As a note for those who are familiar, recent work on NERF and coordinate MLPs tells us that these neural representations can be improved by adding a Fourier features embedding at the input of the network, but we found good performance for a simple task even without it. Once this network is initially trained, its weights are then frozen. Now, throughout this talk, when we mention optimizing the metasurface, we're referring to utilizing auto differentiation and back propagation of the gradients through this frozen MLP in order to optimize the set of shape parameters, that is, the nanofin width Wx and Wy at every location on the metasurface. Lastly, I want to highlight that there are other trainable functions that could be used as implicit representations. In this paper, we considered a few other options for this work. In addition to the MLP, we tested the use of a set of multivariate polynomial functions to represent the mapping, in addition to using elliptic radial basis function networks. These two other representations both require less computation per inference, but in all cases, we found that these other methods had substantially less accuracy. You can see this in the panel below, and only the MLP was able to reproduce the sharp details in this slice of the dataset. Now, before we continue further, we could take a moment and answer one of the initial questions that we raised about the polarization multi-image paradigm. Given the design of the camera and the use of a polarization-sensitive metasurface, what is the channel capacity of this imaging system? In other words, how many coded images can we directly engineer and measure? Let's recall that in the spectral case discussed previously, the answer was unambiguous. With the red, green, and blue spectral filters, we could clearly capture 3 distinctly coded images, since different wavelengths of light do not interfere with each other. In the polarization multi-coded imaging scenario, the answer is less clear because we'll have to consider the interference of polarized light. In this discussion, let's simply assert that the number of distinctly coded imaging channels accessible to us corresponds to the number of intensity patterns that we can independently design when our cameras illuminate by a beam of light. This situation is qualitatively shown below. For conceptual simplicity, let's also approximate the polarization-sensitive metasurface as a pair of independent idealized phase masks. Each phase mask will impart different phase modulation to one of two orthogonal linear polarization states, say 0 or 90 degrees. Now with this pair of phase masks, we know that we can independently design the intensity of the photosensor simultaneously for 0 or 90 degree light and retrieve the images I0 and I90 as shown below. This is simply a holography problem. We also have to remember that light has a phase when it arrives at the photosensor in addition to intensity, and for this discussion, these quantities are important to keep track of, so we'll store these. Now with these four quantities defined, it turns out that the intensity pattern on the other two channels is fully specified. In fact, the intensities I45 and I135 can be reparameterized in terms of the interference shown by this equation. The question that we are left with then is this. If we fix the intensity distributions on these two channels, I0 and I90, can we still control the intensity on the other two channels, perhaps by optimizing the interference? Now, unfortunately, the rigorous answer is no. By specifying the intensity of the aperture plane and the sensor plane for either 0 or 90 degree light, the phase of that light is specified everywhere. And so in the strictest sense, the channel capacity is only 2, meaning we should probably only ever use 2 images in our post-processing algorithm. Alternatively, more important than the rigorous answer is the practical answer, which is yes, if we can make compromises. The idea is that for each of I0 and I90, there are an infinite number of possible intensity patterns that approximate the target distribution that we want. Each one of these realized solutions also has a different output phase, which will produce a different interference effect. In other words, the task of designing a third channel is actually that of sampling from the space of possible intensity pairs on I0 and I90 and finding the one that minimizes the approximation error versus all 3 target distributions. Now, one important subtlety to know in all this is that when we compute the intensity at the sensor plane, we do so over a finite domain of that subspace, which we call the simulation region. When we optimize a metasurface, it is then possible to get different approximations in 2 qualitatively different ways. The first is that we might learn to scatter light outside the simulation region, particularly when our loss function compares the produced intensity versus the target only up to scale. And the second is that our optic might keep all light focused in the simulation region, but will produce errors in the approximation intensity versus the desired one within that finite domain. For use in imaging tasks, we actually prefer to encourage solutions of the second type, since the first would result in a diffuse background that lowers the contrast of our images. We do this during grade descent by using a regularization term in our loss function that penalizes energy that's scattered outside of the calculation region. Now we demonstrate these ideas in a simple task, and in this case, suppose we design a metasurface that produces a pair of intensities on 2 polarization states, I0 and I90, that will approximate a uniform disk of light in the simulation region with a minimum error. The results of this are shown here, and I45 and I135 then follow as a consequence by the interference of 0 and 90. Alternatively, let's now suppose that we also specify a target intensity for the 45 degree polarized light, that is the Harvard crest, in addition to the uniform disk of target for 0 and 9 degree light. By simply allowing for approximation errors on I0 and I90, we could then structure I45 and obtain 3 engineered intensity patterns as shown here. We are also able to do this while keeping most of the light, in this case 90%, within our finite simulation region. So the key idea is that as long as we're able to accept approximate patterns versus exact patterns for intensity, we can increase the channel capacity to 3 instead of 2, thus matching the limit of the equivalent spectral coding method when using a Bayer filter mosaic. In general, this is acceptable because in computational imaging, and especially end-to-end design, we only really care about learning optical codes that enable performance for some reconstruction task versus producing any particular exact set of patterns. Given an understanding of the system and how to optimize the metasurface, we now want to demonstrate its usage by applying it to a new task introduced in this paper called multi-image synthesis. An overview of this design problem in its simplest form is depicted here. Given a scene, we desire an arrangement of nanofins on the metasurface, which will produce some polarization encoded intensity pattern at the photosensor. This intensity is then measured with the polarizer mosaic pixels and is digitally demosaicked to obtain a set of 4 distinctly coded images, I0, I45, I90, and I135, all obtained in single exposure. We then compute only the linear pixelized sum of the 4 images with some learnable scale weights alpha in order to obtain a new synthesized image. This synthesized image can then approximate a spatial frequency filtered rendering of the scene using only a minimum of 6 floating-point operations per pixel regardless of the filtering kernel. Now this problem is closely related to and is inspired by research on optoelectronic image processing that was started in the late 1960s. In contrast to the goals of using optics to reduce the computational cost of filtering, we are however interested in reimagining this problem for 2 different reasons. The first is that implementing general optoelectronic image processing filters, as shown here, presents a previously unsolved hardware problem. A compact, as in a single lens, snapshot implementation that works for general scenes has not been achieved before. Moreover, it's a problem that cannot be solved with spectral coding and requires a transition to polarization. Specifically, the key idea is that in the spectral case, if we are to subtract 2 or more images and hopefully cancel out the signal, we need to be ensured that the ratio of energy in each image channel is the same for any scene. This, of course, is not true in spectral coding because there's no way to ensure that the amount of light emitted from all points of the scene is the same on the 3 wavelength bands. Alternatively, this fact is true in our polarization system when the scene emits unpolarized light. It can also be enforced for any scene by adding a linear polarizer at the entrance of the system, as shown previously. This idea is one of the key advantages of using polarization over spectral coding. Now, our second motivation of this problem is that we can demonstrate new processing functionalities never previously shown. Specifically, in the past, only a single optical filter, defined for a single depth or wavelength, was applied in the synthesized image, which is not in of itself particularly useful. In this work, however, we show that one can create synthesized filters that have a prescribed wavelength dependence or depth dependence. In other words, the filter that is applied in the synthesized image will depend on properties of light that are not directly measured by a photosensor, and thus this method can serve as a technique to produce sparse optical cues. We also showed that instead of applying a single filter, we can code multiple filtering operations in the captured images and selectively apply them by only changing the summation weights. We now show some of the results from the optimizations for this task. We first began with the case of applying different filters by changing only the digital summation weights. An important idea here is that the filtering operations encoded by our camera can be fully defined by specifying the points per function. The points per function is the intensity produced and measured at the photosensor in response to an ideal axial point source. In this case, we can simplify this task by assuming the point source to be in the far field and by considering monochromatic light. Because we have 4 polarization channels, we may say that our camera is characterized by a set of 4 points per functions, as shown in this diagram. Moreover, we can then compute the linear pixelwise sum of these 4 points per functions, like we did for the images in the last slide, in order to obtain a synthesized points per function. I won't derive it here, but it's easy to check and see that the synthesized image mentioned before actually corresponds to an all-focused magnified image of the scene convolved with this digital synthesized points per function. In other words, this net points per function is analogous to the usual filtering kernel of computer vision, and the convolutions are being done for free by the optics. The design task can then be formulated by computing the loss between the synthesized points per functions added through some set of weights, alpha 1 or alpha 2, as shown here, and the target filters. In this case, we focus our attention to a class of steerable filters, and we desire one set of weights that yields a Gaussian derivative along one axis, and another set of weights that yields the derivative along another axis. We then backpropagate gradients to optimize both the metasurface shape parameters and the summation weights. Lastly, I want to highlight that a key part of solving this problem and a large part of this paper is directed to the topic of regularization, although I won't have time to go into great detail here. Besides enforcing light efficiency and avoiding the aforementioned case of light that gets scattered outside our simulation region, we also have to deal with something known as the minimum bias factorization. The idea is that finding a set of 4 positive points per functions that can be added together to produce our positive and negative valued kernel is essentially a constrained matrix factorization problem. Although there are infinite solutions, it ends up that not all are equally useful in real life, and we need regularization to find the good ones. In this paper, we derive and introduce a new regularization term, which basically says that if 2 points per functions are to be subtracted digitally, they should be orthogonal signals. And this condition is something known as the minimum bias signal. Without doing this, it is likely that the filter operation will not work when in the presence of measurement noise. After running the optimization, we then learn a metasurface like that shown on the left. The metasurface implements 2 different phase profiles, Vx and Vy, which results in a set of 4 points per functions shown at the bottom. You can see immediately, but the camera has learned to encode the left and right halves of the Gaussian derivative on the 0 and 90 degree polarized light. It has also learned to produce, by leveraging the interference channel, the Gaussian derivative along the y-axis. The synthesized points per functions for the 2 explicitly learned summation weights, alpha 1 and alpha 2, are shown on the right. The convenient property of this target filter pair is that when these 2 weights are defined, we automatically know the synthesis weights that results in the derivative along every other rotation, as shown by alpha 3 and alpha 4. We display in simulation at the top what the form just captured on the system would look like for a scene that contains the cameraman. Notably, the coding is subtle as it corresponds to a minor blur and a shift of the image by small distances. However, when these images are linearly combined, we obtain the derivative of the scene at any angle that we choose and for an absolute minimum computation cost. Again, using a loss based on the points per function, we also show that one can optically encode frequency filtering operations that have a prescribed depth dependence. In this case, we chose the task of producing a Gaussian derivative with an orientation that rotates with respect to depth. To do this, we consider a set of actual point sources at different distances, and we compute the set of component points per functions and the synthesized points per function for each case. We then optimize for a single set of synthesis weights alpha and a metasurface that minimizes the loss taken between the stack of synthesized points per functions and the target filtering kernels. The results of this optimization are shown here. As a note, although we optimized over all 4 points per functions, the camera learns to use just a pair of images due to subtleties of the minimum bias regularizer. In other words, it learns to set certain terms in the alpha weights to 0, which is actually the best solution for operating under noise. The two component points for functions are shown on the left for several distances within the optimization range, and they synthesize an approximation to the rotating Gaussian derivative filter. On the right, we show in simulation the use of this camera for imaging a toy scene consisting of uniform intensity disks at different depths. By subtracting the two polarization-encoded images, we then obtain the digitally synthesized image, where each object has a different orientation for the applied derivative. By identifying this orientation, we can easily estimate the distance of objects. We highlight that producing an equivalent image using only digital processing of a standard camera image would be very difficult, as it would require first computing a depth and then a segmentation mask. Alternatively, by optimizing optics in this multi-image system, we obtain this result within a minimum of 3 floating-point operations. Lastly, we present on a method to engineer the synthesized filters with respect to wavelength. To successfully do this, however, we found it necessary to move away from a loss based on points per functions and instead use one based directly on the synthesized images. Specifically, the optimization starts with a hyperspectral data cube describing a scene, projected here to RGB for visualization purposes. We then compute for each wavelength channel in the considered range the set of 4 component images that would be obtained in addition to the corresponding synthesized image. We then compare these synthesized images to the desired filtered image, which are specified by the user for each wavelength channel. This loss is then computed on the batch and is minimized to learn the metasurface and the summation weights. While there are many different wavelength targets that we could have looked at in this paper, we actually focus attention to the task of producing a wavelength invariant Laplacian Gaussian kernel. The reason is because a wavelength invariant filter is the simplest task that we can ask for, but be ensured is impossible to realize exactly. This principle of circumnavigating impossible requests is a key idea for this particular optimization algorithm. Although we know that we cannot produce the underlying filtering kernels exactly, we aim to learn the closest set of synthesized filters that approximate our target operation. In other words, they are those that produce synthesized images with similar statistics to those underlying the target transformations. Before I show some of the results, I first want to highlight for review why we know that a wavelength invariant operation is impossible. Besides the fact that field propagation from the metasurface to the photosensor is itself wavelength dependent, the biggest reason is due to the fact that metasurfaces are dispersive. We showed this before, where we know that the phase and transmittance imparted by a metasurface changes substantially with respect to wavelength, as shown here again. This feature of metasurface optics can actually be a useful thing, however, because it implies that we have some ability to structure the points per function with respect to wavelength. At each location on the metasurface, we just need to find the right nanostructure with a particular wavelength dependence. In practice, however, our control is rather limited, and we're constrained to a set of dispersion curves like those shown in the slice from the nanofin dataset. Now moving on, for the optimization, we show in the paper that we can actually learn approximate transformations for the imaging system using a single synthetic data cube for the scene radiance during training. In this case, we use a cameraman image which emits light equally on all wavelength channels in the optimization range. Running this optimization, we then learn a set of component points per functions and synthesized points per functions, which are clearly not a Laplacian Gaussian kernel, but ultimately produce a similar effect edge detection as that shown in the bottom panel. Lastly, we show that this learned lens can then be applied in a zero-shot setting to real hyperspectral scenes using radiance data from the ARAD1K hyperspectral dataset. Of course, the results can be substantially improved by using a real dataset like this during training, although one can get away with synthetic data. Finally, I want to highlight that while most of this talk has presented similar results, we did validate the camera architecture and design principles by building a prototype system as shown here on the left. The camera includes an off-the-shelf polarizer mosaic photosensor. We then fabricated and tested 2 different metasurfaces as shown in the center and found close agreement between the set of 4 extracted points for functions and the simulated intensities for both cases. Using the lens that implements the steerable Gaussian derivative, we also captured images of various targets as shown on the right and confirmed the ability to steer the Gaussian derivatives. In conclusion, we highlight a few takeaways. First, metasurfaces excel at polarization and to a lesser extent wavelength transformations and can be useful for multi-code imaging systems. Moreover, polarization, like wavelength, can be used as distinct multiplexed imaging channels, and in this talk we discussed the channel capacity. Lastly, metasurfaces designed for multi-code imaging systems have the potential to minimize or reduce the computational cost for a wide range of tasks. Regarding the future, it is also worth emphasizing that the ideas of polarization and spectral multi-code imaging are not mutually exclusive, although we presented it in such context in this paper. Specifically, commercially available cameras combine the two and pair the mosaic of linear filters with the RGB8 filters as shown below. This presents an interesting future avenue of research, as metasurfaces would still be an ideal optic to design. Notably, the main limitation of this technique is a limitation to spatial resolution. However, it is well known that this can be fixed by smarter algorithms and demosaicing networks that leverage statistical priors. And lastly, by combining polarization and spectral coding using such filter arrays, it is then possible to simultaneously capture 16 distinct images in a single snapshot. What researchers choose to do with all those images is left to be seen. Thanks for listening to this talk. If you have additional questions or thoughts, feel free to email the authors. Also note that all the code used for this work is made available in addition to an open source inverse design software called DFlat. DFlat is built on both TensorFlow and PyTorch and provides a repository for auto-differentiable implementations spanning the full end-to-end design pipeline. You can access on GitHub by scanning this QR code or by clicking on the links in the page. Thanks again.